Okay, here's today's catalyst. I'll give you guys a second to go ahead and figure this out, and then we'll start on today's lesson. Alright, so today we're going to look at an introduction to gases and stoichiometry, just to refresh a little bit on our stoichiometry when it comes to gas laws. With gas laws, a lot of this will be review, almost all of it will be math. So just as long as we're paying attention to what our variables are, it shouldn't be terribly difficult for us. So let's start here with some general properties of gases. You should have seen these before, but just to review, you should know gases have mass. They take the shape and volume of their container, of their entire container, not just the bottom of the container, although they are affected by gravity. Gases are compressible because their particles are really incredibly far apart from each other, and that will play into some other things here in just a second. And gases exert pressure by colliding with the sides of their containers. And this last one here, because the motion of gases is random, every gaseous mixture will become homogeneous if left alone. So if you mix two gases over time, eventually they'll become homogeneous. Gases are compressible. This is different from liquids and solids, and it's a very specific property to gases. So I have the ability, as shown on this image to the right, to take gas and compress it into a smaller volume when we apply pressure. Okay, so this is going to lead us into what's called the kinetic molecular theory, or the KMT, as you'll often see it referred to. There are 5 postulates, or sort of 5 statements that we make about gases, and this is what we're talking about when we're looking at ideal gases. So later we'll do some calculations with the ideal gas law. What we're doing is we're making some assumptions about the behavior of gases. And not all of these assumptions are true, but they will get us close enough, right? It's not worth our time to do all of this math if we can use something like the ideal gas law and get us sort of within a reasonable range. So here are the 5 postulates. Number 1, the volume occupied by individual gas particles is negligible. We assume that gas particles take up no space. And this has a lot to do with the fact that gas particles are so far apart from each other that we can sort of ignore their volume whenever we're doing calculations. Number 2, gas particles experience no forces of attraction or intermolecular forces. They do experience these forces, but again, because gas particles are so far apart relative to their size, that force of attraction that they feel at that distance is negligible. Gas particles are in continuous, random, and linear motion. This is true. It's called Brownian motion. It's just sort of random. They're in a linear motion. They travel in a line until they are in the collision. So our 4th postulate is that the collisions are elastic. And what that means, essentially, is that we don't lose any energy in the collision to light, sound, or heat. So, for instance, when you think about 2 cars colliding, you lose energy in the form of heat and sound. And so we're assuming that when gases collide, we don't have that heat or sound, when in actuality we do at a very small level. And then the last thing here is we say that the average kinetic energy of a gas is directly proportional to the temperature in Kelvin. Okay? And again, this is our ideal gas law. Gases behave like this under ideal conditions. Right, so here's our ideal gas balloon, right? The reality is that gases don't always behave this way. Gases often behave non-ideally. And if we need to correct for those deviations, we do. If we're working in industry or if we're working in a lab specific to gases or compression, then we need to sort of correct for that behavior. But generally speaking, on the level of high school and college, you don't need to really look at those deviations mathematically. But they do tend to deviate at high pressures and low temperatures. And you are expected to know this. And the way that I've always tried to remember it is that it is a non-ideal time around winter when temperature is low and academic pressure is high. Right? So we say that as non-ideal. And that's just a way for you to try and remember when gases behave non-ideally. So here's a practice problem for you here. Oh, actually, let's go back because this is going to play into our practice problem. The other time is when we have really high masses. So then we come into this problem here. Argon deviates from the ideal behavior at extremely high pressure more than neon does. Which of the following is one reason for this difference? So take a minute, hit pause, try and answer this question. Okay, so the answer here is A. The particle volume of argon is greater than that of neon. So all things about neon and argon are the same with the exception of particle volume. Okay, so let's look at Graham's law of diffusion here. You used to need to know this mathematically. The AP curriculum has since sort of removed this as a mathematical requirement, but you still need to understand conceptually how this works. So when we're talking about Graham's law of diffusion, diffusion is used as a term to define the mixing of gases. So if I take two gases in a container and release them, Graham's law helps us to calculate the rate at which the gases will mix. So mathematically, again, that's not necessary for you to know, but conceptually, here's what you do need to know. That the rate of the mixing is dependent upon the size and the energy. So yesterday and over the weekend, you guys looked at a POGIL talking about the Boltzmann distribution, the Maxwell-Boltzmann distributions here. And so this is the model number 2 coming out of that POGIL. So its rate of diffusion is dependent upon the speed at which a particle is moving. So if two gases are at equal temperatures, the gas that is the lightest has more particles moving at a higher speed than the gas that is the largest here. Right, so helium being the smallest, the lightest particle, its energy can go into moving more quickly, whereas for xenon being very big and heavy, it will take more energy to move, thus having a lower speed. Okay, so again, these are called Maxwell-Boltzmann distributions. We're going to look at this a lot when we come back to reactions, but I want you guys to see this now in terms of gases because I want you to understand something very important, and that's that not all gas temperatures are moving at the same speed, even if they're at the same temperature, right? So I have here, this shows you helium, that as I increase my temperature, the number of particles, 1 million particles, will change its speed. Now, not all of them become faster, but you see that the majority of the particles shifts to different speeds, right? As I get warmer, I have more particles moving quicker. And so this is just like a probability distribution showing you if you're given this many particles, how many of them are likely to be moving at these given speeds. Okay, but that's an important thing for you to understand, that not all particles of gas are moving at the same speed. Some are moving very, very, very quickly. Some are moving very slowly. But the majority of the speeds are dependent upon the temperature. And as you saw in the last image and in this image here, as I heat up a gas, a majority of the particles sort of shift. This distribution shifts to demonstrate or to reflect a change in the majority of the speeds of the particles. Okay, so let's talk about pressure here. So pressure is caused by the collision of molecules with the walls of a container, so it's force over area, right? Force per area. These are all the pressure units that we come across. We're really concerned with atmospheres. Atmospheres, millimeters mercury, and torr. We see PSI in America, pounds per square inch, on our bike tires and on our regular tires. But generally speaking, it's not very common to use pounds per square inch. We are currently under standard pressure, right? Which means that right now there's 14.7 pounds of air pushing on every square inch of our body, right? That's what standard pressure is. And so for ease of calculations, we call that 1 atmosphere, or the air pressure at sea level. If you are interested, you can look up the barometer. The barometer was invented by Torricelli. That's where we get the units torr, and he looked at air pressure using millimeters of mercury, using this glass tube full of mercury. So that's where those two air pressure units come from. It's from Torricelli's barometer. Standard temperature and pressure is something that you need to know. It is listed on your equations page, your reference sheet. So if you go and you find this, you have your big list of variables here, and then underneath it you have your gas constant and then STP. Here are some pressure conversions for you. They're here, and then STP is right here. Notice that STP is listed in Celsius, but we do our calculations in Kelvin. So you need to know that it is 273 Kelvin instead of 0 degrees Celsius. All right, so let's talk for a moment about Avogadro. So Avogadro spent a lot of his life working on different gases and just investigating gases, and he found this, and this is really important. He found that equal volumes of gases at the same temperature and pressure contain the same number of molecules, right? So he's saying that if we keep our conditions of temperature and pressure the same, volume is directly proportional to moles. At low pressures, remember we can't deviate from sort of that ideal gas, otherwise this falls apart. So here's our Avogadro's law. We're not actually going to calculate using Avogadro's law, but it allows us to do something really interesting later. It leads us to molar volume, right? So we know that any gas, right, at standard temperature and pressure, 1 atmosphere, 273 Kelvin, will occupy 22.4 liters worth of volume. And that's that same idea that volume and the number of moles is directly proportional, given that all of our conditions of pressure and temperature remain the same. So here's Mole Mountain again. We've looked at Mole Mountain, and we can review some Mole Mountain more whenever I get back. But here's what this allows us to do with Mole Mountain. Our relationship between moles and liters now becomes sort of a 1-to-1 ratio. So if our conditions of temperature and pressure stay the same, our mole ratios can become our volume ratios. So if this is our balanced equation, right, here's what it is with moles. We can now say with liters that that ratio is the same. And you can prove this to yourself. Instead of going from liters to moles to moles to liters, you can now just go liters to liters. But I encourage you to do some of the practice problems and just see for yourself. Okay? I'm going to let you've got 4 more practice problems that I want you guys to work through and discuss with each other. You can find these answers online if you really need to look them up. But give it a shot, and I will see you guys on Thursday.